Everyone, today I'm starting with that center of pressure. The first experiment is center of pressure. If you already have watched that introduction tutorial, then you know that what type of experiment we'll cover in this tutorial series. So in that introduction, the first one was the center of pressure. So now I'm gonna start the center of pressure in this tutorial series. I'll cover all these necessary calculations, theories, equations, and graphs as I mentioned before. So I'll do the same here. So let me just explain what is a center of pressure. Center of pressure is a point, right? Is a point on a body that is already immersed in a water. And then at that point, all the liquid pressure force acts. For example, we have a body like this one. We have a bucket, or let me just quickly change it to that one. Okay, if we have any body here and the body is submerged in a liquid and it is like this is the watermark, right? This is the body. Now it's kind of horizontal. Okay, so what will happen? We know that there will be hydrostatic pressure, right? And the pressure distribution will be what? We know the hydrostatic pressure increases like this way. If it is following this one, there will be 0 and it will be this one. Okay, so center of pressure will be inside that water body and it will be located somewhere here where all this pressure from the water will act. So that is called center of pressure. For horizontal body like this, the center of pressure will be locating at a point where the center of gravity is located. So center of pressure and center of gravity will be coincide, right? So that will be coincided for horizontal body. But for inclined like this, if we have any body that is inclined surface, is already submerged in the water, but then you may have this CG here, center of gravity, where the center of pressure will be located here, CP. It will be below the center of gravity. Why is that? I'll try to explain that one as well. And now the main theory behind this one is nothing but that hydrostatic pressure distribution I just mentioned here. Because of that hydrostatic pressure distribution, if you go downward like this, we know hydrostatic pressure distribution is this. Pressure increases with the increase in depth. That's why if you go inside ocean, right, for 1 kilometer, 2 kilometer, human skull or your head will be like crushed like a egg. So that is why we need to understand what is the effect of center of gravity, why it is necessary for engineering purpose, right? That is called hydrostatic pressure distribution. If we know that this is the height h and here we have water surface, so that the point where it is atmospheric pressure means it is air, but there won't be any pressure because of this water, and this pressure is called gauge pressure. If you just try to see the pressure inside a tire of a car, you will see we need a gauge to measure that pressure. That is called gauge pressure, right? Gauge pressure. And if you sum the gauge pressure with the atmospheric pressure, means air pressure, then you will get what? Absolute pressure, right? We know this. Absolute pressure is a summation of atmospheric pressure plus that and the gauge pressure. So we'll measure only the gauge pressure because of this water here, and then we'll locate this one from the water surface, where it is located from the surface of the water. Because if you go inside, we usually measure everything from the surface of the water. That's why in this case, we'll measure the center of pressure from the surface of the water. And if you know the total depth of the structure, you can easily calculate the other, right? It will be h minus y cv for necessary calculation and for the designing purpose. So that is called the center of pressure. For inclined surface, it is located below the center of gravity, and for horizontal surface, it is the same as center of gravity. So how can we theoretically determine the center of pressure, and how can we determine the center of pressure using the experimental setup? and then we'll compare both and which is greater than other. So that's the objective of this experiment, to determine the center of pressure theoretically and experimentally, and to compare them, and then we'll finish up with necessary plotting. So the experimental setup here, it is like this. It is called toroidal section. It is a rectangular section and it has a bend. It is kind of showing a quadrant of a circle. You can see here, right? This one, it's a rectangle, and the same length, it is the length here, and here it is the height. It is same. It is called L. Okay. How can you measure that? I'll tell you that one. At first, I'm just showing you the theory. And before going to this experimental setup, I can explain why the center of pressure is necessary for engineering purpose. Let me just quickly show, if you want to design any dam or any kind of hydraulic structure, so what do you need? At first, you have to check if the dam is stable or not. You have to check the stability against overturning, against sliding, and other, right? So, and there is another one, piping. So that is another issue, but for this structural purpose, we need to check the stability based on overturning or sliding first. So let me just quickly show you that one. For example, you have a dam, and general structure of a dam is this one. It may be concrete dam, or it may be earthen, whatever it is. We have a dam. Okay, the structure is like that, and it has its own weight. That is mass mg, mass of this. If you know the unit weight of the material, you can calculate the mass if you know the density, right? If you multiply by acceleration due to gravity, you will get the weight of the dam. That is the force, and this force will act directly downward direction towards downward. And then what will happen? See, for example, if we have water, why we use dam? To hold water, right? At the upstream, we have water up to this height, and if you know that is the height, for example, the height is h. Okay, the height is h. And what will be the pressure distribution? As before, it will be like this. We have the pressure distribution like this, like this. So what will be the total resultant pressure? It will be, for example, it is just F. Okay, total amount of force, or the resultant of this pressure is F. So what we need, so that force will locate at the center of pressure. Sometimes it is the same as center of gravity, or sometimes it is different than center of gravity if the surface is inclined. And here, if we assume this is a point like a hinge point, so what will happen if the water force is higher than the self weight? Then the dam will be washed out. It will push, right? It is pushing from left side. It's pushing the dam from this side to that side, from left to right. If the weight, this weight is not enough to be stable there, then the dam will be washed out. So how can we test that? We have to check by calculating the moment against this point O, right? If it is pushing, since it is pushing from this side, it may be overturning, considering this point as a hinge, O point, and this weight will resist that. The weight of the dam will resist that, and we know that this weight will act through the center of gravity, and usually it is located right at the middle of the body. So here it is. So let me just take moment. So this force will go this way, and it is generating a clockwise moment. However, this one, it is going this way, and it is generating anti-clockwise moment, right, around this point. So that is our moment point. We can take moment at O, and if we consider that, okay, clockwise moment is positive. So at first, I'm taking moment against this force. This force is same. It is just passing this way, same. So what will be the height? This height, right? If you know the center of pressure YP, if you know the total height, it is basically Y. y is equal to h minus yp, because we measured the center of pressure from the top and then we deduced that from the total height, and then we got this distance or height or depth from the bottom of the dam. We know the y. So now y is the moment arm, and what will be the moment? So this moment will be overturning moments. That's why I'm calling it MO, right? MO, here it is. And what will be the value of the moment? It is force into the moment arm. So what is the force? F into y, right? F into y here. That is the moment arm, and it is clockwise. That's why it's positive here. I mentioned it is positive. And then we have another moment because of this weight this way, right? So that is anti-clockwise, negative. So W into the distance. If you consider this is the distance from that O point is G, then that one, there is no other moment or force, so it is balanced condition, then it is 0. So we can, right, calculate force, or we can calculate y, anything from this one. Okay, and that is the equation we will use in our experiment. But for example, the moment we just calculated, MO is equal to Fy, and Mr, that is Wg, resisting moment. So for balanced condition, the dam won't be washed out, right? So the condition is MO is equal to Mr for this depth of water H. Considering all these situations are similar, but if something happened, then definitely MO may be greater than Mr. If somehow the moment, that is overturning moment, is greater than Mr, if the depth of water increases, then definitely this value of y will increase. If the value of y increases, then definitely this value will increase, right? And it will be greater than resisting moment, then the dam will be washed out. It will fail by overturning, right? Because of this overturning moment. So that's why we can check if the dam is stable or not. So because of testing that one, our resisting moment Mr should always be greater than Mo. How can we do that? We can increase the size of the dam, and then the volume will be increased at the same time. Because of that, the total weight or the mass of the dam will be increased, and then it will be stable. It will be stable. So this is how we can check if the dam is stable or not, or any other hydraulic structure. To check the stability, we need to calculate that center of pressure. So that is one practical application, and we can use that center of pressure anywhere, right? So we'll use the same principle in our experiment to calculate the center of pressure oppositely. So that is the setup we have. It is called toroidal section, as I mentioned before. So that O point, consider that same O point, it is this one, hinge, right? We have a hinge here, hinge point. And from this one, from this hinge point, we have weight here, right? We have some weight from this point to this point. That is the G. We just measure that G. And what will happen? It's a glass box, a rectangular box, and inside this box, we have this toroidal section. The same rectangular section continuing as a bend. It is a quadrant of a circular section. So that's why it is solid as well. It is solid. So what will happen if we just pour water? If we fill this box with water, then something will happen. So what will happen? Let me just explain that first. So considering the same principle we mentioned, what will be the experimental setup? How can we measure that center of pressure? So at first, since it is a instrument, right, and it's a kind of setup, and we can move this setup from one place to another, you can see we have different, right, legs. At first, you have to balance it. You have to balance it using that spirit level here. You can see a bubble. You have to balance it. When it is perfectly balanced, then we'll add water. Then we'll add water. But before adding water, what do you have to do? You have to use this wheel. You can just rotate it either clockwise or anti-clockwise and remove this one. At first, remove this one, and then here you can see one mark. You can see one leveling there. If you see, you have to removing this one, removing this mesh, and just tuning this wheel clockwise or anti-clockwise. You have to fix it. You have a marking there. If you see it's level, then without adding water at first, if you have the leveled instrument from the bottom and the instrument is always should be balanced before adding water, because that is the hinge. If you just move this thing to this way, it will go up, and if you just move it this way, it will go down. So this is how we have to fix that level before adding water. So that is the preliminary condition. So now we have a device or instrument that is perfectly leveled and it is also balanced, right? Then we're just trying to intervene. We're trying to disturb this system, balance system, adding water. So we are adding water. We have a drain valve here. We're just closing this one for the time being. We are adding water, okay? We are adding water, and we are filling water either this way or here. If water is here, that means see, this total height is not emerging. It is not submerged. It is partially submerged for this condition. So we'll check two different conditions. If water is here, then we'll have this depth, and if water is here, we'll have this depth. So that is called fully, right, submerged. And for this one, it is partially, okay, it is partially submerged. So we have to be able to calculate what will happen if it is partially submerged and what will happen if it is fully submerged condition. So we'll check different types and then we'll plot. So this will happen if you just change the water height, and then we have to take readings. What type of reading we'll take? Let me just explain. So that is the setup. It will be done for two different types of conditions, partially submerged and fully submerged. And for each of this condition, we have to calculate the center of pressure. And you have to plot how it is changing, right? So when you are adding water, you will see that water is pushing, right? Pushing this, and the system is again imbalanced. Then, for example, you have water here. You fill this box with water up to this level, then it is imbalanced, right? This is going down and this is going up. This is going down. Then you have to make it balanced again here, adding load here. You have to add weight one by one, this one by one, until it is again balanced as before. When it is balanced, then you have to take reading, right? This reading, you have to take reading. How can you take the reading? So it is already there. So you can see the scale. Here it is. So what type of reading you need to take? You need to take, you have to consider everything from the surface of the water. See, this is the surface of the water. You have to measure this one, this depth, whether it is partially submerged or fully submerged. Consider all this measurement will be from the surface of the water. So that will be Y1 from the surface of the water to the top of the turtle box or the turtle section, that is Y1. And from the surface of the water to the bottom of the turtle section will always be Y2. Consider that. Keep in mind, all the measurement will be from the surface of the water, and from the surface of the water to the top of the box or the section will be Y1, and then from the water surface to the bottom of the section will be y2, right? And for partially submerged condition, what will happen if water is filled up with this way? Again, I'm just showing all together, that's why it is this. If water is here, then from the top, again, it is y1, and from water surface to the bottom, again, it's y2. That is the measurement. And what we have to take again, see, that is the center or the hinge point. So this distance, since it is a section, this is called small r, and from this one to the outer radius is called capital R. So this R and this R is same. From here to here, it is also capital R, and from here to here, it is also capital R. So these are same. So that's why if you want to measure this distance or this height, what do you have to do? The L will be capital R minus small r. So you can take a scale or measuring a scale, and you can measure distance from this part to this part, that is also small r, and you can measure distance from this part to this part, because you can't have access to this section because it will be inside water, inside the box. It is difficult. That's why it is same. So you can measure, this is capital R, this is small r. I have the measurement. I'll show you the calculation, everything. So once you have capital R and small r, then you can calculate the L, right? And we'll fill up the data sheet as well, right? That is the preliminary, that will be same for everyone, every group. If you have different groups, right, that will be same for each of them. So what we are calculating here, center of pressure. First, for submerged condition, water is here, we are measuring y1 from this one and y2 from water surface to this one. So what will be the pressure distribution here? See, the pressure distribution will always be like this as before. For submerged condition, our pressure distribution is this, and we're gonna calculate the center of pressure. It will be somewhere here. Okay, means from the surface of the water to this one, yCp. So that is our goal, to calculate the center of the pressure, right? Because the force, total force, will act at this point, but we don't know the location, right? We don't know the location. So that's what we have to do. We have to apply the same principle that we applied. We have to determine the center of pressure yCp theoretically and practically. So how can we determine the center of pressure theoretically? See, for this one, we know the center of gravity for any rectangular body, right? Center of gravity, it will be located here. If water is here, then definitely if you go inside, if that is the height, so it will be h/2. We know this, right? And if you want to calculate the same distance from this axis, right? Your body is here. You want to calculate the same distance from here. That is called for example, that is called yCp, right? So that is Cg. So for this one, what is the Cg? yCg is h/2. That is from the top, this axis, right? X-axis, that is x bar. We are just transferring the axis. If you want to calculate the center of gravity from that x prime axis, so we know the axis transfer formula, right? The theory, we know that. So that is why I'm just assigning this distance yCp. So yCp will be that y bar, means the center of gravity from the previous axis, plus we have to know the moment Cg, right? The moment of inertia about the centroidal axis, because these are the centroidal axis, we know that. And then again y and a, or a y bar, whatever it is. Usually we just give this way, a y bar. So we can easily calculate, right? If you know the value of y bar, because we know it is h/2, and you know the area, if you know the b, and if you know h, it is bh, you know the area, bh. And then only thing you need to know that ICZ. For rectangular section, right, ICZ will be bh³/12. We know that moment of inertia of a rectangular body, right, along the centroidal axis. So that is ICZ. If you know ICZ, you can easily calculate ICP. So that is the theoretical calculation of center of pressure. So same calculation, since it is the section is rectangular here, you can see it's a rectangular section. It is if you see from this side, if you look at from this side, you'll see it's nothing but this one. It is nothing but this one. So sometimes now it is fully submerged, water is here, it's completely inside water, right? But what will happen, because see, water force is only working there, right, here. So if it is fully submerged, then we have to consider L. If it is partially submerged, if water is here, you have to consider only those part that is covered by water. Then it will be this part. It is y2. So that is the thing you have to keep in mind. For fully submerged, even though the water is higher than the length of the body, you have to consider only L, because we are calculating the forces acting on the rectangular surface. But if it is partially submerged, means it is not completely under the water, it is partially submerged, water is covering only this part, then you have to calculate only those part, right, this height, and you know the B. That is the difference between partially submerged and fully submerged condition. Okay, so let me just, so I already mentioned this one, theoretical determination of center of pressure this way. We will directly use that calculation. Now YCP is equal to y bar plus I CG over a y bar. If the section is fully submerged, since the section is like this, we know the length is L, means height is L, for example. That's why we call it length, because see, this is length and same as the height. So we are calling it as L. L, we know this L is equal to R minus R, capital R minus small r, and that is the B. We know that B, right? If it is fully submerged, water is here, means this condition, water is here. Then for the calculation, we'll only assume this box. So what will be the y bar then? Will be L by 2, right? And what will be A? A will be BL, okay? What will be ICZ? ICZ will be BL cube over 12. Then we can easily calculate YCP directly for fully submerged condition, okay? For fully submerged condition. So what will happen if the condition is partially submerged? Now water is not covering the entire body, means water is somewhere here. For example, I'm changing that. So for example, water is here, okay? For this case, water is here. So we are measuring this distance from the top of this, that is the y1 now, always. And from water surface to the bottom of this, it is always y2. So for partially submerged, see, y2 is the height of water that is covering that section. So keeping in mind, it will be like this. Water is here. It is only y2. This is y2, and that is y1. That is y1 because we have water here, and always it is b. Water is here. So what will be y for now? It will be y2 divided by 2 because now the center of gravity will be here, right? Noted here. And what will be a? It will be b y2. What will be I CZ? It will be b y2 cube over 12. So now if it is partially, we can use this form. If it is fully, we can use the full section to calculate YCP theoretically. Okay. Theoretically, we can determine this way. So that is the theoretical determination of center of pressure. But now, how can we determine the center of pressure using our experimental setup? I just explained. Yeah, we can calculate R, we can calculate, right? We can calculate small r, we can calculate capital R, and then we can calculate L. And yeah, we'll pour water, we'll fill up this, we'll make the balance using weight here. So we'll measure that weight, how much mass we need to make balance of this system, right? Because what will happen? Why we are balancing this one? So water is pushing this way because of this buoyancy force, right? So we have this box. This box is like this way. This is the box, upside is open, and we have this section here. We have this section here, located here. When you are just pouring water up to this one, so water is pushing from this side, water is pushing from this side, right? And water is pushing from the bottom. So this left, this right side, and this left side, these are counterclockwise, counterbalancing each other. So there will be no effect from this side to from this side and this side. Only, right, this force, buoyancy force, that is just imbalancing the system. That's why we're adding weight here. We're adding weight here to make it stable and making it balance again, right? Because we're balancing this one, adding weight. And then we're measuring only the horizontal pressure, see, the force that is acting here. Only remaining part is this part. We're balancing every other extra forces, and we're measuring the center of pressure only because of this horizontal pressure distribution here. So once the system is balanced, you already have taken reading for capital R, you already have reading for small r, you calculated that L, and you already calculate, right? You have the calculation for Y1, whatever the level of water, you know the distance from water surface to top of that choroidal section is Y1. If it is partially, it is same Y1, and that is Y2 from the water surface to the bottom of the choroidal section for fully submerged, and for partially submerged it is this. So we know this calculation. We have the weight, we know this values from the experiment. So now once we have the balance system, because that is the hinge we have, that is the hinge we have, and we have this weight, and we know that that distance is G, as before we just demonstrated that practical application, right? We already have idea. When I calculated the stability of a dam, then we use this G, and this G is from the hinge to this one, W is equal to mg. W is equal to mg, okay? And then what we have now, from this hinge, we have to calculate the distance of the center of pressure, right? Center of pressure. Let me just quickly remove all this thing, and I'm considering, okay, that is the center of pressure, that is F, total force acting, and from this, okay, from this we're calculating this distance Y. So we have F, we have the moment term y, and we also have this g, and we also have this mg. If we take moment around, at this point, what will happen? This force F, this F, it will be clockwise, and that mass, it will also be anti-clockwise for this point. So okay, taking moment, because the system is balanced, we added weight such a way that it is balanced. We can see a marking here, it is balanced. Then let me just write the same equation that I wrote for the dam, right? For this point and for F, it is clockwise, positive. So F into Y, right, minus, for weight, it is anti-clockwise, this one anti-clockwise, and momentum is G. So W into G. Since it is balanced, we can make it 0. So Fy is equal to Wg. So from this one, we don't know Y. So Wg and over F. See, we can calculate W if we know the total mass here. We can know the total mass. We'll know the total mass, and then we can multiply this Ng G and then F. And we need to calculate F. How can we calculate F? Because we know that if we have any distribution, pressure distribution this way, we know pressure here, it is P0, right? And since it is hydrostatic pressure, so here, if it is like Y, what will be the magnitude at the bottom of the distribution? It will be gamma Y, or rho G Y, right? So gamma is the unit weight of water, and G is and rho is the density. We can, gamma is equal to rho G, we know that. And then the total force for this section will be the area of this triangle. This area of this triangle will be the total force, right? So how can we calculate that one? We know that the area will be half of that Y into rho G Y. So it is half rho G Y square. But this is, see, we're just calculating. For example, here we have the pressure distribution, this one. This pressure distribution is basically at a certain point, and we have the width, right? We have the entire width, this one. This line here, you can see this distribution is at a single line, this line, and we have to go further, we have to cover, right? These are everywhere. This distribution is everywhere. If you want to calculate total force on this, so we need to calculate this line. This line is what? This line is this one. And for another line, we will have another half rho G Y square. And if you just multiply by that B, then you will have total force for that plane, rectangular plane. That's why for calculating total force, what we need, we're just making average of Y bar. So rho G, Y bar, and A. Okay, that means rho G, if we just use that Y square, okay, Y square, because we have half here, and B, that one. So from this, what we can write? We can write F is equal to Y over 2 into rho G into Y into B. So Y into B, what will be that? Y into B. If you know that that is the B, and if it is Y, so that is the area, okay? That is the area. So that's why an Y over 2, if that is the Y, if that is Y, so what will be the Y bar, right? Y bar will be Y by 2, we just mentioned previously. So that's why it is nothing but rho G, Y bar, and A. So for total force, for calculating total force, we are using this formula. F is equal to rho g y bar A. So if you know F in this equation, right? If you know A in this equation, because you already have y, this y is equal to this one. So y is equal to mg and g divided by F. We know F, right? Already F from that equation, that rho g y over A. And we know g from the measurement. If we use scale, we can calculate this one. I'm just going to show you all this calculation. If you know total weight, because you know how much weight you added here, and you know the value of G9.81, okay? And you can calculate the y. So from y, so what is y? Y is nothing but this distance from that top to the center of pressure, right? For center of pressure. Let me just make it clear here. You know y. And now what do you need to know? You need to calculate the center of pressure, this one, YCP from the surface of the water, right? For example, for fully submerged condition, now it is fully submerged condition here, fully submerged condition, you know this y from that equation we just saw, you know y. So now we have to make another equation depending on the situation. We know y from this to that, we have to calculate YCP. How can I do that? So y, this one, this will be equal to, right, the same distance, this is small r, right, and it is also same for this one, small r, it is also same. So we can write y is equal to small r, right? Y is from here to here, we have to move even from here to here using our known values. We know r from this one to top of this one, you know, it's r, right? We are here. And then what we know y1 from here to top of the water surface, so that is the negative minus y1. Now we are at the water surface, and from water surface we have to go to the center of pressure using that YCP. So from YCP, from that equation YCP, we can easily calculate y, right? If we just move from left to right, so y minus r plus y1. If it is fully submerged condition, then we can use this equation. And if it is partially submerged, right, we don't have this line here. Now it is, for example, it is partially submerged condition. So what will happen? For example, it is partially submerged condition. Now it is not fully submerged, it is partially. We calculated that F value as before, the same from that equation. Now we have water here, okay? We have water here, we have pressure distribution, like this, all these are same. We have to calculate, because it is the total force, we have to calculate that YCP. Now YCP is here from the surface of the water. So that is the y1 again, and that is y2 again, water surface to bottom and water surface to top. And we also know r, right? R is same here, and r is also same here. We know this is r, and we know that y is from here to the center of pressure, because we applied that theory. So that is y. So we know y again for partially submerged condition. Let me just again use the similar logic here, okay? When the system is partially submerged, we know y, this one, equal to, we can move from this one to this one, right, r, and now we are here, we can go from this point to water surface, plus y1, now we are here, water surface, and now we need to go up to YCP. So YCP is equal to y minus r minus y1. So when the system is partially submerged, we can use this formula to calculate YCP, And if it is fully submerged, we can use this formula to calculate YCP. So this is how we can calculate experimentally by balancing the whole system and by taking these readings of Y1, Y2, and mass on the pan and the moment arm, and then we can calculate Y, and then we can use this formula for partially submerged and fully submerged to calculate YCP. And we already have idea about theoretical determination of YCP, right? So now let me just show you how to calculate once we have this, right? Once we have all this data set, let me just show you that. See here, I'm just showing the same thing. You have to calculate this G distance from here to here, and then R, this is the P, R is this, capital R is this, and we are measuring all this distance from the water surface, Y1 from top to the water surface, Y2 is from, this is not right, this will be up to this one. This is the partially submerged condition, and fully submerged condition is for this picture. It is same. We're applying the same condition. We just demonstrated. Let me just show you that. We'll discuss this equation as well, right? Why the center of pressure is below the center of gravity for an inclined surface. Okay, I'm giving the answer not right now, but before that I can show the sample calculation. So here are the data that we collected from practical class. These are the actual value. So the small r for that setup, it is 10 centimeter, this one. And for the curvature, that is bigger one, it is 20. And the width, right, this one, this width, it is B 7.5 centimeter. So what will be the height, this height, L? It is nothing but 20 minus 10 is equal to 10 centimeter, okay? 10 centimeter. And then G, what is the G? That arm, we already know that it is 27.5. And for a condition that is partially submerged, we collected this Y1 is 1.9 and then Y2 is 8.1. Since Y2 is less than 10, because we know it's 10, right? The height is 10, this height is 10. Since it is less than 10, definitely it is partially submerged condition. Now we have to calculate this now Y bar, F, ICZ, and then we know the mass for this. This is group number 4. Okay, let me just that is 150. Okay, this mass is 150. So for this one, we'll calculate that YCP theoretically and practically. This is theoretical and this is experimental. So let me just calculate this way. At first, we have Y1, 1, Y2. So what we need for theoretical determination of theory, okay? Theoretically, what we can do, we know the equation YCP is equal to Y bar, means the center of gravity, plus ICZ over a Y bar. So for partially submerged condition, right, we know that for partially submerged condition, when water is there, Y2, water is filling up to this one. So what will be the Y bar? Y bar will be Y2 over 2. That means what we have? We have 8.1 over 2, 8.1 divided by 2, 4.05, right? 4.05, all are in centimeter. So this centimeter is 4.05. We know that Y bar. Then what will be the area A? A will be BY2. We know B 7.5 into Y2 8.1. So 7.5 into 8.1 is giving us 60.75. The area, this is in squared centimeter, okay? What will be ICZ? We have to calculate that, okay? ICZ, it is B Y2 cube now, right? Over 12. That means it is nothing but 7.5 into 8.1 cube divided by 12. So what will be the value? it is a 7.5 into 8.1 cubic power divided by 12. Okay, so we have a 332.15. This will be centimeter to the power 4. This is ICG. So we know all these values. So y bar is 4.05 plus 332.15 divided by area is 60.75 into 4.05. So what will be the theoretical determination of YCP? It is this one divided by 60.75 divided by 4.05 plus 4.05. So that's that 5.4. Okay, so we have 5.40 centimeter. So we can fill up for theoretical determination is 5.40 centimeter. Right, we have ICG 332 here. It is also centimeter to the power 4, 332.15. right, that is the determination we have. And now we need to calculate the experimental. So the condition is partially, okay, it is partially submerged condition, partially. So for this one we need to calculate F, we need to calculate Y, and then we can apply that equations we just mentioned there, and then we can calculate. Okay, so let me remove that one. The condition is partially. Now we're gonna calculate from the experiment. Okay, we have to calculate that F into what? Fy is equal to Wg. So from these we have to calculate Y. So Wg divided by F. We need F. How can we calculate F? We just mentioned that one. Rho, G, Y bar, and A. Right? We know rho, since all are in centimeters, so we have to apply rho means the density of water. Density of water in CGS means 1 gram per centimeter. Okay, 1 gram per centimeter cube, and Z 981 this centimeter per second square into Y bar is 4.05 centimeter, right, into A is 7.5 into, since it is partially submerged, it will be Y2. Y2 is 8.1. So these are basically centimeter square. So if you just calculate 981 into 1 into 4.05 into 7.5 into 8.1, it will give you that 2.4 into 10 to the power 5. This is called dynes in terms of, if you use all unit in centimeter and gram, it will be dyne. So 2.4 into 10 to the power 5 dynes. That is the amount of force we have, right? And then because we already calculated this part in the equation directly, we don't need to use that again. What we need to calculate now? Y, that one. So we can calculate Y using this. So we know the mass, right? We know the mass in terms of gram here, 150 mg. So it will be mg, J, and F. So what is M? 150, and then G again 981, and then this is 27.5 centimeter, this G, and F we know 2.4 into 10 to the power 5. Then we'll have Y in terms of centimeter. Okay, so 150 into 981 into 27.5 divided by total F. So we have 16.765 centimeter, right? So that is the Y from the pivot point to the center of pressure, right? So for that case, let me just show you again that one. Again, right, we have, since it is partially submerged here, see, we know this y. We know this y now, this y from the line, that is from the same line, and we have to calculate y Cp. So we know y, we can calculate y Cp from this one. So what will be this one? So y is equal to what? We are now from here to here, but we can go from here to the top of the toroid r, that is r, and then we can use y1, then we can go to water surface, and then can we use y Cp. So y Cp is equal to y minus r minus y1. So what is y? We have 16.765 minus small r is 10 minus what is y1? Y1 maybe 1.9. Yeah, it's there. So this one minus 10 minus 1.9. So that is 4.86 centimeter. This is theoretically 4.86. Okay, 4.86. So we have this 16.765 and 4.86 centimeter. So we calculated theoretically, we calculated practically, right? And what we can see here, the theoretical determination is greater than this practical value. So that is the theory. You know, theoretical value is always identical, and the practical is there will be some errors, right? You can measure, there might be some parallax error, there might be some other error, the density of water may change, the room temperature, it will be different. So that is the ideal condition. That's why it's right greater than the experimental value. So this is how we can calculate. So I just calculated for one, I calculated for one reading for one group. So if we have more group, right, see, we have group number 1, for example, here their mass is huge and their y2 is 15.5. that means it is more than 10. The height of this section is 10. It is fully submerged. So and then they have more weight, it is also fully submerged. Then they have this weight and is also fully submerged. For this one it is partially, for this one it is also partially submerged condition. So if we just want to see how it varies, right, how it varies, so then we need to plot it. We need to plot the mass on the pan against y2, the depth of water. Then we'll see this graph. See, this graph is showing along the x-axis the depth of water. If you just increase the depth or decrease the depth, and you see the mass on the pan. So the limit for this experiment is we know the height, right? That is the section 10, that is the 10, we know that, we measured that one. So here is the 10. This line is the demarcation line for 10. Means when you just adding water, when water is here, then that is the red line we have. So less than this 10, less than this, it is partially, right? It's partially, and when water is more than this, it is fully. So that's why all these points that are located on the right side, that are fully submerged condition. Okay, that are fully submerged condition, and here these are partially submerged condition. These are partially submerged. Okay, so this is how we can see the how it varies with the depth. So the relationship, it is not linear, it is non-linear. If you just extend it up to 0, it will be like non-linear. Okay, it is non-linear relationship. That's that we can plot. And okay, let me just answer some questions that we see here. So discuss why the center of pressure is below the center of gravity for an inclined surface, because we know that because of this hydrostatic pressure increases with the increase in depth. That's why for inclined surface, the center of pressure will locate just below the center of gravity, but for horizontal surface, the center of pressure and the center of gravity coincide. Okay, that's the answer for the question number 1. And what is what are the practical application of the center of pressure? I already mentioned that one, to check the stability of any hydraulic structure, for example, the dam, and for designing any retaining wall, we need to check the stability. And for reinforcement design, we need to calculate the moment. And for calculating the moment, we need to know the moment arm and where the total force is acting. We need to know the center of pressure. That are the practical application. And if a triangle of height d and base b is vertical and submerged in a liquid, derive an expression for the depth to its center of pressure from the liquid surface. That means we have a liquid surface here and we have a triangle, right? We have a triangle this way. We have a triangle this way that is completely immersed in a surface, and they're deciding that, okay, the base is b and then the height is d. So they are asking, okay, if the center of pressure is here, it is see inclined surface, it is inclined surface, we'll have the answer. So they're asking what will be the value of Cp. We have to express this. Since we don't have any exact value, we'll determine, right, in terms of d. So we know that for a triangle, if you have already taken that mechanics course, so you already know what is the center of gravity, because we have that theory. YCP is equal to y bar plus ICG over a y bar. That is the equation we'll use. And then we need to know the area of the triangle. We know the area of the triangle will be BD divided by 2, half into base into height. And then we need to know ICG and we need to know the y bar. So for triangle, we know that the CG, for example, CG is here. The CG will be located 1/3 of D from the base and 2/3 from the top. So since we are calculating from the top, it will be 2D divided by 3. So that is the distance y bar from the center. And what is the area? We know that. And ICG, we know for a triangle, ICG is base and the height divided by 36. So these are the information you need to know beforehand. You can check and it will be there in the mechanics course. So if I apply that, YCP is equal to 2/3 2D over 3 plus and BD divided by 36 divided by A BD over 2 into 2D over 3. And if you just simplify, what will happen? It will be this way: 2D over 3 plus B D cube divided by 36 into 2 divided by BD into 3 divided by 2D. Okay, so if I just neutralize, so this 3 and this 3 would be neutralized, and then we can even calculate. Okay, we can check. See, no, we can't do that because it is plus. Okay, just let me 2D. Okay, 2D over 3. So 2D over 3 is same plus this 3 and 2. This will be 6, and that will be what? 6. And this B, okay, this B and this B will be neutralized, and this D square, and this D cube will be D. So what will we have? We have D as numerator, and denominator will be 6 into 2, 12, right? So if you just simplify, it will be 12, and then it will be 8D plus D. That means 9D over 12. So 3 over 4D. So YCP is what? So we got YCP as, right, 3 by 4D means 75% of D. But what was the center of gravity, 2/3 d, right, from the top. So y-over was 2/3 of d, and that is the 66.7% of d. So which one is deeper? Of course, yCp is greater than y prime. So that's why the answer for this question is this. For inclined surface, it is inclined, right? This surface is inclined. So that's why for inclined surface, the center of pressure is located below the center of gravity. And we already know the practical application, and we already have idea about this one. So in this experiment, what we basically saw, we know the equations, necessary equations, and we know what is center of pressure. Center of pressure is a point where all the forces, basically the water forces, act, right? We calculated the center of pressure from the surface of the water from experimental setup, and using that theoretical equation, this equation, right? This equation. And we saw that the center of pressure from theory is greater than experiment. We already checked for partial condition and now fully submerged condition as well. And we see the plot that varies the depth of water, that varies with the mass on the pan. And we saw the relationship is not linear. So that means if you increase the depth, you don't, the mass won't be like linear. It will be a non-linear relationship. So once you are done with this one, you can write your report. So our objective for this one is to determine the center of pressure theoretically and practically. And we already know how to determine and what are the practical applications of center of pressure. Okay, so you can now write your report based on, write your report. You can do that, and you can finish your submission as well at the same time. You can submit that, and we can move forward. So that's that. We're just trying to even see the next tutorial we have, and we can even move forward with the Bernoulli's principle. Okay, we'll do that in the next tutorial, the Bernoulli's principle, and we'll show the same type of calculations and graph as well. So that's that. I'm gonna finish here, and if you have any query or any question, you can even let me know. And you can use this data, because these data are real data that has been collected from laboratory setup. So this will help you to understand the calculation and the basics of this experiment. So thank you very much for watching, and stay safe and take care.